Hey guys, welcome back to AlgoYogi. Now we are doing graph series, and our next problem in the list is path with minimum effort. Let's go to LeetCode and solve this problem. Okay, so it's a medium level LeetCode problem. You are a hiker preparing for an upcoming hike. You are given heights, a 2D array of size rows and columns, where heights, row and column represent the height of the cell, row and column representing the row and column, basically the position of that hill. You are situated at the top left cell, which is right here, 0, 0. Right now you can see it's 1, and on and or right, and oh, and you hope to travel to the bottom right cell. Okay, rows are basically to 5 where we want to travel. Now you can move up, down, left or right. So from A you could go up, down, or like consider 8. From here you can go up to 2, 3, 2 and 3 right here. And you wish to find a route that requires the minimum effort. A route's effort is the maximum absolute difference in height between two consecutive cells of the route. Now we need to return the minimum effort required to travel from the top cell to the bottom right cell. So top left cell to the bottom right cell. So basically what we want to do is we want to get from 1 to 5, but you cannot go diagonally. You can only go going left, right, top, bottom. So from 1 you can either choose to go this way. So this is one path, then you could go this way, that's another path, this is another path, this is another path, or from here this is another path. So nothing diagonally, but like you could keep choosing these different paths. Okay, these different paths. So you can already figure out like there are so many paths possible going from 1 to basically 5. Now we need to choose the path that has the minimum effort. So doesn't it sound familiar that we've just studying Dijkstra algorithm, where we are trying to find from the source. This is the source right here, source, and this is the destination, and there is some cost for while visiting from this node its neighbors, because that's how you reach all these connecting neighbors. That's how you visit, so but there is no direct cost here, but there is kind of, because they told us there's something called effort from going from hill A to B. So there is going from some hill A to B, there is effort, which is the absolute difference of height A minus B. So this is what we need to minimize while traversing, and that we have to do it for all the nodes that we choose to take from 1 to 5. So let's say if I choose this path right here. So I'm just gonna delete this again. So let's say if we choose to take this path from 1 to 2, so the difference here is 1. The effort here is 1. Here the effort is 0. Here the effort is 0. Here the effort is 3. So what's the maximum effort that you have basically taken? So the max would be 3. So this path has the max effort is 3, and this max effort is what we need to minimize. So this path has the effort 3, but let's say if we choose some other path, let's say we choose path from 1 to 3. So basically the effort from 1 to 3 is 2, because that's the difference. From 3 to 5, that's also 2. From 5 to 3, the difference is 2. 3 to 5, this is also 2. So if you see right here, the max effort that we have seen so far is 2 in this path, 2. So this is actually minimum to 3. So this is a better route for ourselves. This is like we want to minimize the maximum difference that you see across all the elements in one path. There could be another path right here, this path, but if you can see the difference between 2 and 8 is already 6. 6 is way worse than 3, and 3 is better than 2, but 2 is the best. Okay, so now since we have already covered Dijkstra algorithm, what we will really be doing here is we're gonna start at our first our top left element. That's the source element, or source node you can say, and we need to get to our destination, which is the bottom right element in our grid. And then we'll have a priority queue. We will be this will be heap queue, and we have studied like how you use min heap, how you basically import heap queue data structure and then add your array to it. So we'll be adding our source, which will be basically, right now its difference is what we are trying to minimize. So difference, or not minimize, we are basically, this is our priority I would say this is the basis for prioritizing our nodes that we choose. So we'll be having a queue that will have this will be our difference, then we will have rows and column. So initially we'll be starting, if you haven't seen the Dijkstra video that I've just created, I'll be posting this video after I have posted that one. So I hope if you watch this in order, then it will be more it will be better for us to understand. So this is what we will be putting inside our min heap or heap queue, or generally an array, and we'll be heapifying that. So that will prioritize based on how we visit these nodes. So initially what will happen is we'll be putting 0, and then this is also 0. So R and C, this is where we start. Now what we're gonna do is we're gonna pop this from our queue. So queue will initially has this, then we will pop this, and then we're gonna start exploring from 1 to its neighboring nodes. So what are its neighboring nodes? This is 1, this is another neighboring node. These are the 2 neighboring nodes. We're gonna start exploring. So what I'll do is I will visit these nodes, and here I will calculate its difference. So while I'm visiting this one, if it is in my bounds, so remember from here I could try to go up and this way also, but they are not in my bounds. So we'll have a bound check. So I will be exploring this too. So what I'll do is I will calculate the difference here. So difference is 1, and then this particular node is basically, so 0 1 2 0 1 2, these are rows and columns. So this row is 0 and column is 1. So this is what I have already popped this out. This is the one that I'm visiting, but I'll be appending it to my queue. I will append this to my queue. Okay, I will append this to my queue. So this is the one I'm currently visiting. So I will calculate this difference. This difference is 1, and then I will calculate this difference. This difference is 2, and I'm gonna now visit this one. So I will also append that to my queue. So the difference here would be 2, and I will add 1, 0. So these are 3 that are in my queue, and I've already popped this out. But remember that, like, at the end of the day, like, we'll keep making these decisions. We'll keep adding all of these, and finally we are making this decision where we'll minimize our effort. So just like the Dijkstra algorithm, at the end we will reach to 5, and we'll have this minimum difference that we have just calculated. So let's write down the solution. I think it will be super straightforward once we write down the code. You will be able to see the Dijkstra algorithm right there. Okay, I'm gonna just zoom in. So as I said, first thing first, let's calculate the rows and columns. That is the length of height. I'm just gonna copy this. So that's the rows length. For column lengths, it's gonna be the length of let's choose any 0th heights. Then we're gonna have a visit set. We'll have a visit set. Then I want to now have our min heap. I'm gonna call it min heap. This is basically min heap is the priority queue. Initially it's gonna start with the first element that we're gonna add is the difference. So right now difference, you are on the very first node, right on top left. So right now the difference is basically 0, but remember, as we explore to the destination node, we'll keep updating this and we'll keep trying to find this. We'll try to find the maximum difference, but then also try to finally minimize the entire, the maximum that we have seen in all the paths. So minimize the maximums of all the paths. So I guess that's clear. So let's have R and C initially starting at 0th element, 0th row and 0th column. Then let's start exploring in our while loop. So while min heap is not empty, let's pop from our min heap. So it's first thing is difference, second is row, and third is column. So I'm gonna pop from our min heap. So the way you do is basically heap q dot pop, not pop, heap pop, and then you just give it your min heap. So I'm sure like it will just like create the min heap using this, and then give you the very first element in this priority queue or min heap, like the minimum that has the minimum difference. Okay, now we have our current node that we need to explore. So let's explore its neighbors. How you gonna do the neighbors? Like before we start exploring this, let's just see if it is in visit set. If it is in our visit set, so if this R comma C in visit set, then what you want to do is you want to continue to the next element, next node to explore. So continue. Okay, otherwise we will add this to our visit set. So add R and C. Otherwise let's have all the directions explored. So I'm just gonna make an array that will store all the directions. So 0, 1, that's for incrementing the column. Now the same way, let's decrement the column. So 0, so first is row, second is column, and we'll be basically exploring it using a for loop and then adding it to our current row and column so that we can find the new row and column. So this will be -1, we are decrementing it. Let's increment the row this time. So 1, 0, and then finally -1, 0. Okay, if you didn't have any idea what I was doing here, you will have now. Okay, so for dr and dc in our directions, let's create the new r and new c by adding so r plus dr and c plus dc. So we have just created these new node basically indexes that we need to explore in our grid. So but like let's just rule out all the out of bounds or already visited ones. So if this new r is it's less than 0, or this new r is greater than equals to our rows right here, greater than equals to rows. Same goes for columns. So new c less than 0, or this new c is greater than equals to our calls. Or there is one more thing, that is if this is already in my visit set. So if this, or not add just copied the wrong thing. So if this R and C, and you know what, it's better to write this way. So new this R and C, or in our visit set. Okay, if any of this happens, that means just forget about it, move on to your next direction that you need to explore. So it might have gone in like, up, down, out of bounds, or already visited. So let's just continue. We don't want a break because we still have other directions to explore. So continue. Okay, but now if we are pass through it, that means we have a nice node that we need to explore, adjacent node. So what we gonna do is, first thing is we're gonna calculate the height difference of our current node to this new node that we could possibly go to. So I'll have a height diff that will be basically absolute of this is our heights, right? This array is height. So heights at R and C minus same thing but with our new R and C. Okay, so new R and new C. All right, so finally, so what we're gonna do here is, let's calculate the new difference. New difference would be maximum of the previous difference that we just calculated. Basically, it's the difference that I just calculated from reaching that node. That is the current node that I'm currently exploring. Either this, I have to see the maximum from all the path that I could explore. So this diff is what we are basically we are seeing this as maximum. Okay, but remember, this priority queue is basically keeping the minimum on the top, so we are maximizing it. So either this old diff or this new diff. Now I am going to append this to my min heap. Okay, so heap queue dot heap push, and I'm pushing to my min heap, and what I'm pushing is the next element, that is the new difference I'm pushing, and my I'm pushing the new R and C. Okay, because this new diff is what can take me to there, because I have calculated the max difference from my current diff and the height difference that I could reach there. Okay, so maximum, either I have already seen this or this current diff. Okay, all right, so that's all, I think. And now the final thing is, we have to either, if we are already like on the last node that we on the destination. So if my R is, or you can check it like this way. So if R and C is equals to this row and column, so this basically, but I'm going to basically, sorry, right here, so this, but I'm gonna basically, because index starts with 0, so I'm gonna decrement it right here. If this happens, that means I can return this diff. I can return this this diff. Okay, I think that is it. Let's zoom out and run this algorithm. We don't have to return anything because I'm sure like it's guaranteed there will be a path, there will be a lot of paths, but at the end, after we'll keeping the minimum difference value on the top because of the priority queue. That's how it happens in our Dijkstra algorithm. So let's run it on our example cases and see if there is an issue. I think we forgot a comma in line 22, which is or. Yeah, of course, this is not comma, this is or. Yeah, these are the very common mistakes that I think I always make while writing this long condition. Let's submit it. All right, so I think with the time complexity and space complexity, there's a lot of confusion and debate going on. So I'm not complexity, I don't know, I'm not gonna go into it, but most likely what people say is it's gonna be m into or r into c, because you're traversing the entire grid, r into c, and then because of the priority queue you have it log r and c. Okay, log r and c, because at max you will be maintaining this log r and c at the this binary tree that you create. But definitely, and I think space complexity will be, since we have this visit set, I guess we'll be adding everything to visit set, so we're gonna have r into c. Okay, this is r and c are the rows and columns. But yeah, this was a crazy solution, and I think we'll be experiencing a lot more crazier solutions as we go forward. I would really recommend if you go watch the videos, conceptual videos of priority queues, Dijkstra algorithm, DFS, BFS, because at the end of the day, this is what we are really doing here is BFS, because we pop out one element and then we explore all its neighbors. This is what we are doing here. And if you go to the BFS DFS video that I've just posted, you'll have a better idea understanding this whole solution. Okay, so let's go to AlgoYogi, mark this problem solved, and see you guys later in the next problem. Until then, bye bye.